Good day. I am Vilma Narisa Angelica Isabel, and together with my groupmates, we are going to explain how to solve an air standard Otto cycle problem. What is an air standard Otto cycle? It is an idealized cycle for the spark ignition internal combustion engine. And for the sample problem, here is Jean Elise.
To approximate an actual spark ignition engine, consider an air standard Otto cycle that has a heat addition of 1,900 kJ per kilogram of air, a compression ratio of 7, and a pressure and temperature at the beginning of the compression process of 100 kPa, 10 degrees Celsius. Determine the maximum pressure and temperature of the cycle, the thermal efficiency of the cycle, and the mean effective pressure. The given are the heat added, which is equal to 1,900 kJ per kilogram, the compression ratio, which is equal to 7, and the pressure and temperature at the beginning of the compression cycle, which is equal to 100 kPa and 10 degrees Celsius. For the required, we need to solve the maximum temperature and pressure, which is equal to T3 and P3, the thermal efficiency of the cycle, and the mean effective pressure.
In Otto cycle, consists of 4 strokes and starts with an intake stroke at essentially constant pressure, during which a piston moving outward draws a fuel or air mixture into a cylinder. This is represented by this figure. During the second stroke, all valves are closed and the fuel or air mixture is compressed, approximately adiabatically along line segment 1 to 2. The mixture is then ignited, and combustion occurs so rapidly that the volume remains nearly constant while the pressure rises along the line segment 2 to 3. It is during the third stroke that work is produced. The high temperature, high pressure products of combustion expand approximately adiabatically along line segment 3 to 4. The exhaust valve then opens and the pressure falls rapidly at nearly constant volume along line segment 4 to 1.
For the first step in solving the problem, we need to find the temperature and pressure at point 2, which will be used later on for solving the maximum temperature and pressure. Based from the diagram Jane discussed earlier, the first process, which starts at point 1 to point 2, is described as a reversible adiabatic compression of air. In order to solve for T2 and P2, we need to use the relationship of pressure, temperature, and volume in an adiabatic reversible process. The equations to be used are from Paris Chemical Engineering Handbook, 8th edition, page 10-44, and equations 10-70 and 10-71.
For computing the value of P2, we have the formula P2 over P1 is equals to the quantity of V1 over V2 raised to K, wherein K is equals to Cp over Cv. Then, P2 is equals to P1 multiplied by the quantity V1 over V2 raised to K. Substituting these values, we have P1 is equals to 100 kilopascal multiplied by the compression ratio 7 raised to K, which is 1.4. Calculating, we have P2, which is 1524.5345 kilopascal.
Then, for solving T2, we have the equation T2 over T1 is equal to B1 over B2 raised to K minus 1. So T2 will be equal to T1 times the quantity of B1 over B2 raised to K minus 1. Upon substituting the values, we will have T2 is equal to 283.15 Kelvin multiplied by the compression ratio 7 raised to 1.4 minus 1. Upon solving, we will arrive at the answer 616.6742 Kelvin.
Now, we're going to find the temperature and pressure at point 3. To solve the temperature at point 3, the equation we're going to use is T3 equals T2 plus delta T from the equation delta T equals T3 minus T2. Since it is shown in the graph that the process at point 2 to 3 has heat addition at constant volume, we're also going to use the equation Q equals CV delta T and substitute delta T to Q over CV. Therefore, the derived equation will be T3 equals T2 plus Q over CV. But before we solve the T3, let's solve first the CV. The CV for air is equals to 5 halves R. The R we're going to use is 8.314 kJ per mole Kelvin. To solve CV equals 5 halves times 8.314 kJ per mole Kelvin. Since our CV is in terms of mole, we're going to convert it in terms of kilogram by multiplying it to 1 mole over 28.96 kg of air. Now CV is equals to 0.7177 kJ per kilogram Kelvin. Let's substitute their corresponding values and then compute for T3. T3 is equals to 616.6742 Kelvin plus 1900 kJ per Kelvin kilogram all over 0.7177 kJ per kilogram Kelvin. Therefore, our T3 is equals to 3264.0199 Kelvin. Since we already have the T2, P2, and T3, we can now solve for P3 in the equation P2 times T3 all over T2 is equals to P3. Substituting the values, P3 equals to 1524.5345 kilopascal times 3264.0199 Kelvin all over 616.6742 Kelvin. Thus, P3 is equals to 8069.2705 kilopascal.
For the calculation of efficiency and net work, we have the V1 over V2 ratio is equal to 7, which is also equal to R. To solve for the efficiency, we used the formula given by Van Ness in Chemical Engineering Thermodynamics 6th edition, page 297, equation 8.6. We have efficiency is equal to 1 minus 1 over R raised to K minus 1, where K is equal to Cp over Cv ratio, which is equal to 1.4 for air. Substituting all the given values, we have efficiency is equal to 1 minus 1 over 7 raised to 1.4 minus 1, which will give the 0.5408 value of the efficiency. To get the net work, given the formula of efficiency is equal to work net over Q, and deriving the equation for work net, we have work net is equal to efficiency multiplied by Q. Substituting all the values given, we have 0.5408 multiplied by 1900 kJ per kilogram is equal to 1027.52 kJ per kilogram.
So now, let's proceed to the calculation. For the displacement volume, we need to find the values of V1 and V2. And to find V1, we will be using the ideal gas law, PV is equal to nRT. Rearranging the equation, V1 is equal to RT1 over P1. Substituting the values, 8.314 kilojoule per kilomole Kelvin times 1 kmol per 28.96 kilogram times 283.15 Kelvin all over 100 kilopascal. Upon solving, the value of V1 is equal to 0.8129 cubic meter per kilogram. For V2, we are going to use the compression factor given, which is V1 over V2 is equal to 7. Rearranging the equation, we get V2 is equal to V1 over 7. So substituting the values, we get 0.8129 cubic meter per kilogram all over 7. Calculating, we get V2 is equal to 0.1161 cubic meter per kilogram. Lastly, we are going to compute for the mean effective pressure. But first, let me define what mean effective pressure is. So, generally, it is defined as the ratio of the net work done to the displacement volume of the piston. Now, we can calculate the value of the mean effective pressure with the formula PMF is equal to work net all over the displacement volume, which is V1 minus V2. Substituting the values, we have 1027.52 kilojoule per kilogram all over 0.8129 minus 0.1161 cubic meter per kilogram. Calculating, we will arrive at the answer PMF is equal to 1,474.6269 kilopascal.
For the recap of the solved values, we have temperature 3, which is equal to 3,264.0199 Kelvin. For pressure 3, which is equal to 8,069.2705 kilopascal. For efficiency, which is equal to 0.5408, and for the mean effective pressure, which is equal to 1,474.6269 kilopascal.
Thanks for watching!
We hope you learned.
Merry Christmas!